Hello, in this lecture, actually it is not a lecture, it is a demonstration or lecture demonstration, where we are going to see how optimality criteria method can be implemented to obtain compliant mechanism topologies based on what we discussed in the lectures. This program was written by my postdoc Lu Zhang In way back in 2002, even the date I have put there, and that still works in the sense that after many years in MATLAB we are able to still use that thing. It was actually written in Fortran, but we have a MEX file implemented in MATLAB and it works. As operating systems are changing, still this seems to be working compiled many years ago, more than 14 years ago. So, this particular one requires an input file, okay, that is in this case I have an input file called gripper.yin. In fact, yin is because his last name, it is input file, Lu Zhang input file, and that is all you need to create an input file for the specification that you are interested in. We look at the input file now. Once you do that, you do not have to touch the rest of the MATLAB code or the Fortran code, that is YinSyn F. YinSyn because Lu Zhang In synthesis problem, YinSyn Fortran with the exclamation that runs that Fortran file, executable file is there in the folder. You will have that executable file as well as sample input files and the MATLAB program. So, these are the three things that you need, and you can run it. As a supplementary file for this course, you will have these to run. You can also download from my website at IISc. So, we will run this now and then see how we get the solution. Okay. So, first let me run. So, we are running it. You can see iteration number 1, 2, 3, objective function which is negative, that ratio of negative MSE by SE. So, it keeps on decreasing, meaning that it is becoming more and more negative, as you can see, minus 4.54, minus 0.55, it is going there. It will converge after some iterations, or we interrupt it after 100 iterations. Usually that is good enough. In fact, 50 iterations are good enough for an optimization algorithm for this optimality criteria method to work. Here it is done. It took all the 100 iterations. Now it is giving the solution. So, you can see what we have put here. So, let us look at the specification. We have taken a domain where there is a hole already, meaning that it is a L shaped domain. We have taken a big rectangle and subtracted a smaller rectangle. Our boundary conditions are that this edge here is fixed, meaning that both x and y degrees of freedom are fixed. It is a 2D implementation, not a 3D, 2D, everything is planar. This is fixed here, and the bottom edge here is symmetric, like a roller boundary condition. All the points here can only move in this horizontal or x direction, but cannot move in y direction, meaning that if I take a mirror image, it will be symmetric. It is a symmetric boundary condition here. We are applying a force here, we are applying a force there, and we want this point to move out like that. So, basically when I push here, this should open up like this. On the other side, if it is a mirror image, it will also go the other way, right. That is the specification. Again we are fixing it here and this. So, with this one we get a topology solution that looks like this. So, let me make it bigger. So, it is fixed here, roller support here, that way circles, and this is squares, that is fixed, and we are applying a force, okay, not over there, I am applying a force here. We can change it to that place also, applying a force in this lower left corner, apply a force, this should move out, and we are given a very small volume. So, lot of elements are in grey color. So, black here means that rho is equal to 1, material is present. Lot of things have disappeared from our design domain here, that is all has gone to rho equal to 0. In between there are a few, giving a small volume. I will show you what volume constraint we have, then you will actually get a skeleton type of structure. Now, when you have this, it actually works. So, if I look at superimposed with the displacement, we get solution like this, that is apply a force here, it is going to move out. You can see that if there is a slender beam element there, slender beam element and little triangle over here, another triangle meaning that it is a rigid body, when apply a force it goes like that, right. So, it could be intuitive for some of you. So, if you try that yourself, you might obtain the same solution from your mind, from your intuition, but here we just get the solution. So, here I have now 5 students of mine or IASC students, so they should be very smart. So, I have asked them to do this problem. So, let us see what they would have had from their intuition. So, I would ask any one of them to come forward and show their solution. So, we can compare what they have versus what the algorithm gave. So, for this specification, so any one of you can come and show your solution. So, again it is fixed here and this is a roller support. So, let us see what solution. Yeah. So, in this case the input is here. So, the input is over here, so this way, and the output is there. So, whereas this algorithm has input there, we will change it. So, that the solution that one of my students Safan Palatingal has gotten is that he is because it is fixed here, he has gotten that, and this is a vertical thing, and when you apply the force like this, he thinks that it goes up like that. Okay. Now, the difference is that the one that we ran, I am applying the force here. So, it took an inclined one, right, rest of it is all rigid. So, he also has put some fillet type of thing here. So, whereas here it is a little bit more, and he has made this here, this is part of the solution Safan? No. So, solution is only this here, right, just 3 beams. He thinks that if you apply that, whether it is correct or not, you have to do finite element analysis and find out. Okay. But now we are just looking at it. Now, let me move that force from here to here and then see what the algorithm does. Okay. Let us go back to the code and look at the input file, that gripper.yin, which I have here. It is a text file. So, it is self explanatory. It first says what kind of element type you want to use. There is a C0 for finite element input and then C1 for finite element input. If you want to C0 continuity, C1 continuity, you are using C0 continuity. Let us not go into the detail of what is C1 continuous finite element. And then if you put mech here, we are solving a mechanism problem. If you put STRU, you can actually do stiff structure problem, because this algorithm is identical in many ways to stiff structure optimization. If you can put stiff structure STRU or mech for compliant mechanism, and you can define the rectangular domain by defining the lower left corner and then upper right corner. So, you are defining a rectangle, and then number of elements along the x direction and y direction. So, since it is 300 150, to have all the elements square elements, which is always preferable. So, we have 64 along the x axis 300 units and then 32 for the 150 units. You can change it, and number of holes, we have put one hole to take off that little thing the right side. So, that is, let me just show so that you are with me. So, this is the hole. Okay. So, we have big rectangle 0 0 300 300, and then we have a small hole that goes from 150 to 150 0, that is this point, and then 375 that point. That is how we can define lower left corner, upper right corner, you can put a hole. You can put a hole inside also if you want. Okay. So, that is what we have, and then number of solid non-designed domains. Sometimes you may want to put material somewhere for sure. So, here we are not putting material anywhere, but that is why it is 0, otherwise you say 1, and you can say from here to here I want to have black, meaning material should be there. Okay. That also can be given, that is called non-designed domains. And number of edges where you want to specify displacements. This boundary condition, you have 2 edges. Again, let us see what those 2 edges are. So, one edge is that, another edge is this. Edge you can give from again starting point, ending point. They can also be inclined if you want, because starting point here, ending point there, you can fix that. It is a very general program, of course without user interface. That is for a reason, because when you are when you want a code to last for a long time, if you put user interface as a version of the program changes MATLAB, things will change. So, here we just have a text version. So, here we have two edges and we give those two edges. So, it says x starting point, y starting point, and then x end, y end, and then displacement component that you want to fix, whether it is x degree of or y degree of freedom. Here it says if it is x degree of freedom 1, y degree of freedom 2, and both of them 7. There are other C1 continuous elements, ignore that, ignore this part 3, 4, 5, 6. So, 1 is for x, 2 for y, 7 for both. So, for one thing we are fixing both, that is the left side top edge that we have. So, that is this one. So, we are starting from 0, 112 something, 112.5 to 150, those are the ones we are fixing, both degrees of freedom, that is why it is 7, and then the horizontal 0, 0, that is 0, 0, 300, 0, that is this point, everywhere we have roller support. Okay. Even though there is a hole, we are still doing it, that does not matter for the program because it is not complaining. And then we have second 2 meaning that y direction is restricted to be 0, meaning that we have a roller support and things cannot move in the y direction, symmetry boundary condition, that is what we have. And then we also have the input port, that is where the force is applied. We have only one of them, you can have as many as you want, and again the x coordinate and then y coordinate, that is what we have, and then 1 1. So, this one is what is the direction, 1 is x, 2 is y, and then sign whether towards positive side and negative side, and then if it is force it is 0, displacement it is 1, here it is a force. So, we have 0, then 5000 is the magnitude, how much force you are applying. Okay. You are applying the force at 0, 0, that is what I had said, that where I am applying force here. Instead let us move it to 150. So, let me put the force here 150. Now, the force point has moved, let me save it. So, force point has moved from here to here, 150 is the x coordinate, 0 the y coordinate, okay, and again it is still in the same direction. Okay. And output also we have only one point, you can have multiple, but one makes sense for us when we start out. And where is it? It is 300, 150, meaning it is the upper right corner, and again it is 2, second degree of freedom, positive direction, and we have 100 as the stiffness of the spring. We will come back to this notion. Without spring, this algorithm will not give a solution all the time. Right now the way it is implemented, you can try, whatever you give you get a solution, as long as input is consistent, that is you will not put a output point in the place where there is a hole and things like that. So, if you give proper input, it will give a solution always. The stiffness of the spring is important, that is output point needs to have a load. We will come to that in the next lectures. We have that 100 here, and material property we are taking Young's modulus some 2 megapascal, number actually does not matter for topology. Poisson's ratio taken 0.3, that matters a little bit, but not a whole lot. And then this penalty factor, that eta that we discussed in the lecture, d equal to rho raised to eta times d0, that is this eta to be taken 3 here. You can try what happens if you change it. And then volume fraction here we have put 0.1, meaning it is fraction 10%, that is why it is very lean. We will change it and rerun it, and lower and upper bounds, 0.01 is lower bound, 1 is the upper bound, that rho has to vary between 0 and 1. Here it is 0.01 and then 1. Know that 0.01 raised to 3 will be 10 power minus 6. So, this is close to 0, and then tolerance for stopping, that is rho k plus 1 and rho k 10 power minus 5, pretty tight tolerance. Okay. This is what we have, let us save this and run the program again. It is running real time in MATLAB, meaning that if we do it in C or Fortran directly, it would be much faster. Of course, it is running Fortran program here on this platform. You can see iteration numbers are just going. If you make it very fine tuned, lot more elements, then it will be little slower, because you have to do finite element analysis at each iteration. Now, it is done and it got a solution. See, it just moved. Previously we were applying there, now it has moved it over here. So, this we are applying the force. Now, compared to what my student did, where he has taken directly from here to somewhere there and he got it down something like this. Now, this is taking a little bit of a rigid triangle here. I said triangle because the symmetry boundary condition. So, it is like a rigid bar is there, the whole thing can move, right, and it is force applied there and it is going like this is coming and it is going like that. Okay. Slightly different, topologically one can argue it is the same, because these all, after all it is rigid. So, he went from here to here and got that one and then made it this move like that, right. So, now the idea is that we can do it intuitively, but you can also do it very quickly using the algorithm. Now, instead of going up like that, okay, now I ask the students to think about what happens if I want this to come this way to the left. Okay, algorithm is a easy thing for me to try. So, I am applying the force over here and I want this point to move to the left like this. What happens? Okay. So, let us run this. Before I do that, just so that they have a little bit more time to do, that is, output now should not go up, it should go to the left, everything else remains the same. Okay. Now, what we will do is, first we will increase the volume a little bit and then see what happens. Instead of 10%, let me actually make it let us say 30%, okay, of the material. All right. So, let us see if the topology remains the same. Okay. For you to see that, what I will do is save one of these pictures, okay, so that you can compare. So, let me take a screenshot and save it somewhere for now, so you can compare. Let us paste here. Okay, I think screenshot has to work. Okay, let me take the solution, print screen. Okay, let's save that. Now, let us go and rerun this. I hope I saved it. Okay, we have saved it, 30% material. Let us see how the topology changes when you have more material. Everything else is the same now from previous time we ran it, only thing is material we are giving 30% rather than 10% we had given. That was a very lean design where you can actually see the skeleton very clearly. Now, it will be a fatty one where you cannot see the inherent characteristic, but the topology, whether it is similar or it changes, we can look at it. Again, it is real time, it is trying to minimize the ratio that we talked about subject to the volume constraint that we have. It is done now. So, show the solution, it is going to change it, it is plotting. So, now let us compare what we got over here versus what we got with 10%. Yeah. So, topologically they are the same, right, because this particular thing is beefed up a little bit, and instead of using a slender beam here, it has now gotten a flexural hinge. We will come back to that another lecture, it is a very important thing. Why does it go for a hinge here, and this beam here is little fattened, we have more food for it because we gave more volume, and again it has a flexure here, whereas here it was like more distributed, and then rest of it. topologically it is similar, okay, that is what we got. So, when you sometimes give a lot of volume, you do not see the essence of the topology. When you give very little volume, you can actually see beam elements or beam segments emerging out of it. Okay. Now, what we will do is we will go back to 10% and change the output direction. Where is output direction? Output per specifications, where we said its second degree of freedom y should go up. Now, I will change it to 1, that becomes the x degree of freedom. I want it to go to the left, that will become minus. So, she made two changes now, volume as well as the output point. Let me save it and rerun this. Let us see what we have. Okay, now we are going to the left. If anybody has tried it, they will show. And you can also try while the program is running, test your intuition or pause it, take your time and see what algorithm comes up with. It has finished. Okay. So, now it has done, it has done its job already, that it came up with a topology like this. Now, what are we doing? Applying a force here, we want this point to move that way. You should have a component in that direction, not saying that exactly it should move in that. If you say exactly it should move, you put a constraint that it cannot have y displacement, which you have not done. So, when this point moves, it will have a component in the left direction. So, what it has done, so we can see here where the deformed plot is also given. This is while moving to the left, it also has moved up. We did not constrain it, that is why it does not do that. If you want to constrain it, you have to physically put a constraint, but that is not allowed. So, you have to put a constraint in the formulation itself. So, you can make the compliance of formulation more and more difficult. I am not saying that I should put a roller here, so that it only moves in the x direction, that will change the boundary condition. Instead, I want a design where without any constraint here, it should move purely in the x direction. If you want that, then you should say that y displacement at that point is 0, and you have to put a constraint in the optimization and solve another nonlinear constraint. People have done that, but this program does not have that. Now, it is also moving in this direction. Okay. Has anybody done this to compare? Yeah. So, let us look at Anusha Pai's design for this. Yeah. So, her design, maybe you need to zoom in a little bit here. So, we are applying a force this way, and she thinks that, yeah, look at this, look at this. So, it is fixed over here, and this all rolling boundary condition. When apply a force here, this moves like that. Okay. So, our intuition tells her that when she moves it this way, it is going to move like that. Maybe your intuition also says, but finally the sanity check would be a finite element analysis, whether finite element analysis will tell you when you do this, it goes like that. Maybe she will have an explanation as to why she came up with this, right. Now, we compare with what we have there. Topologically, it is hard to say, because the algorithm, if you see, let us compare with what the algorithm has. Algorithm has this point over there, just as she has taken. She also has taken the lower edge to be the support, and then there is this portion which is vertical, which this also has. It goes like that up and it comes. Maybe it is kind of similar, right, because if you say that this all what she has taken as just one segment, it may be right. So, you can look at that. Okay. So, now we will immediately change this. Now, what if I want it to go that way, or what it goes down? Okay. Let us try that one more change here, one more change. So, I will say that now the point has to move down. So, let me go back to the input file. So, I will go back to the y displacement. This is the output port specification. I go back to y degree of freedom and then say it has to come down. Previously, we had asked it to go up, now come down. Let us see what we get. Saved it, let it run. And we will run it with finer discretization we changed the volume and saw that there is not much effect in terms of topology. Now, we can also make it finer and finer, where it will be so fine that you can take it and 3D print it today. Okay? That is it is possible to do that. You just have to do image processing of this and 3D print. That was the idea with topology optimization. You do not have to give algorithm anything other than the specifications, it figures out everything, gives you a solution. Okay. But there are nuances, the point may not really move strictly in the y direction as we saw in this example. Okay. So, it is going to, it is finished, now it is going to change the images. Okay. It came up with an image, so which looks a little complicated, but one can argue why it does in a particular way. We are applying the force here, it took another support like last time fixed here, and then now this point is moving down. Let us see, if I enlarge it here, we can see that it is indeed moving down. Okay. It has a little x displacement also, and let us see what one of the students has come up with. Okay. So, study the solution, it is a little complicated, it has taken a lot of segments, whereas the one that again Safan, a PhD student, came up with is this, where we have fixed here. Algorithm also has taken at the lower edge, just as he has taken. So, he has an algorithm in his head and apply the force here, and this has to come down. So, he has taken this and that and that. I do not know why this particular shape. Okay. I am sure he has a reason for it. So, if he thinks that if you apply the force here, this is going to come down. There is really no restriction here. Sometimes some points may not even move, right, but here I presume that he has taken this segment also. So, the segment is from here to here to here. This particular shape of the segment, he has some reasoning, he probably has some reasoning. Similarly, you may have your own reasoning. When you do this, it is going to come down, is what he is thinking. Algorithm did not take this segment over there, it actually took from here, created a complicated loop and took another support back here, as you can see the thing. So, sometimes may agree with your intuition, sometimes it does not, but every time it will give a solution. In fact, you can take this and put in all directions and then see what happens. Okay. So, now what I will do is we will try to make this with much finer discretization to see what happens. So, I go back to the input file and we have, you can see also how fast it does, right. So, we have 64 elements and 32. Let me make it 128 elements and this has 64 elements. Okay. That is a lot of variables. Variables are 128 by 64. Since it is MATLAB, we can get that number 128 times 64. So, we have 8192 variables here, row 1, row 2, row 81, 92. Let us run this now. Let us save this and run this now. It is going to take a while now, as you can see, because finite element analysis is the one that takes more time to run. Okay. You can see first iteration, you can see that it taking time, right. Previously it was just zipping through 100, but it takes a little bit of time. Okay, while it is running, let us look at the input file, output file one more time. So, we can again identify some of the features that we need to discuss. One is this stiffness of the spring constant of the output. Okay. So, here if you do not have that spring constant, then you have a lot of points in our design domain. If you do not put a spring, what makes the output point special? You have input point where there is a force and the algorithm knows that where the force is applied, it knows, meaning that it has obligation or mechanics is such that it has to connect to that point. Whereas, if you do not put an output load or output spring, then the point that you have in mind is not any special compared to any other point. So, algorithm may or may not make connection to that point, which we will do by decreasing the spring constant. This number is arrived at by playing with whatever we have put the numbers here. Let us say instead of 100 I put 0.1, then it may not even make an attempt to connect to the output point, because that output point is same as any other point on the boundary or inside, right. There is nothing special about the output point. So, we need to have a stiffness spring in this ratio formulation, which I did not mention the lecture, but that is a practical aspect. There are many other ways to achieve the same thing. So, first thing is that it is a compliance and stiffness formulation, that is one thing, that is we are maximizing the output displacement and trying to minimize the strain energy or have an upper bound on the strain energy. Additionally, we also need to have an output load or an output spring, because a compliant mechanism output will always act against some loading or a spring load like an object, elastic object or this, but there could be problems where there is neither an output spring nor an output load. How do you do that? Like in rigid body linkages we can also pose this. So, to avoid that, to avoid this need for the spring constant, there have been attempts to get different formulations which we will discuss in one of the lectures, but you note that that is an important thing. Okay. Other than that, everything else is very straightforward here. You have to define the design domains and put a holes there, what edges you want to fix and what is the material that you want to give, and the penalty factor you can play with that penalty factor, you can reduce it, increase it and then see, and tolerance you can do it, it will go little faster. Now, with all this talking we are still in the 43rd iteration, it is going to take a little bit more time. You can keep on doing it. Now, we had originally we had 64 and 32 elements, now I put 128 and 64. If you want you can make it 256 and 128, push the limit of your memory. So, or whatever is coded in this Fortran file, right. You can, right now there are 8000 variables and you can see iteration it is just taking a few seconds. Okay. It is slower than what it was for a coarse discretization, but still not bad. Each iteration you should know that we are doing two finite element analysis, one with the real load, applied load that we have, other with the unit virtual load. Okay. So, that is how the time is going, not in the updating and the inner loop to determine this lambda and gamma, right. So, all of that is happening as when it goes from let us say 56 to 57, two finite element analysis and the update to find the to satisfy the volume constraint here, which is just linear. In fact, here we do not have lambda and gamma, we only have lambda corresponding to the volume constraint. Okay. And you can challenge yourself by creating a very complicated specification here, and so far I have not seen a case where the input is consistent and solution was not obtained. If you have a problem where you are not getting a design, you should send that input file to me. Okay. Right now this is gripper.yin, you can save it whatever name, and all you need to do is in MATLAB file you have to just put the name of that file. So, over here we need to just put the name of the file, everything else is just reading the input or actually the when you run the Fortran code by reading input file here, it will generate a lot of output files, this boundary condition, some output, input specifications and lots of other data, all that is used in this MATLAB program to simply to plot it. It is most like a post processing thing. If you look at the data here, so if I just go okay, so let us see, let it run. So, you can see the data files, there will be a lot of these data files that are created when it executes this thing. Okay. Your input file holds the key, we are nearing 95, it is let to go to 100 iterations. So, 96, 97, 98, 99, 100, it goes 101 because the first one is not counted, and we get the solution. Okay. It took a little longer because we made a finer discretization. It is going to plot it in a minute or less than that. Lot more to plot, even the plotting is now slowed down. So, again the specifications are applying a force and it should think come down, that is what we have asked. Okay. It has done, yeah. Now, the finer discretization you can see, and this has plotted. Okay. Now, if you see, we can go to little finer and actually see there is no, I mean some of these things will go away, the gray ones will go away, or it will be a weak mesh there. We have a beam, we have a beam, we have a beam, we have a beam, we can actually put beam segments. Somewhere here it still wants to go for a hinge, we will talk about that. There is a there are two elements that are diagonally connecting here, it wants a hinge here, a flexural joint, rest of it is there, and the topology has not changed. Whatever we had earlier, we did not save it, but you can run it again, and if you apply the force there, it is coming down. Okay. So, I have taken only one example, but I encourage you to run a lot of examples. All you have to do is go with this input file and change it, and once again when you try something, any specification and you do not get a solution, send it to me, because it is supposed to work all the time. It has been working for dozen years or more. Okay. But make sure that your input file is consistent. Again, if you put a hole here, do not ask for output displacement there or apply input force there. Such things you have to check when you give the specifications for it. All these files will be available to you as part of the supplementary files, and the theory we have discussed and everything is implemented for you to play with. Thank you.